In this video, I introduce unsupervised reinforcement learning and auxiliary learning. Value-based reinforcement learning, such as Q-learning, approximates the state action value Q using a convolutional neural network with parameters theta, and then updates theta by minimizing n-step look-ahead loss, as shown here and explained in this figure. This value network and this target network. Where theta bar are previous theta and the optimization is with respect to theta. Policy gradient method finds the optimal policy that maximizes the expected reward using the policy gradient as shown here. A3C approximates the policy pi and value function v using the parameters theta, as shown here. This environment, this copies for each actor. The learner is used to update the policy parameters theta. Output is a policy distribution and value function. Both the policy and the value function are just towards the n-step look-ahead value, as shown here. And here, this is the loss A3C, which consists of three terms, namely value replay loss, expected reward, and the entropy bonus for exploration. Given a set of auxiliary control tasks C, pi C is the auxiliary task policy for C, and pi is the base task policy. The overall reinforcement learning objective is to maximize the total performance across all the tasks as shown here, where R is calculated from gamma and RC is a discounted return for auxiliary reward RC. Pi and pi C share the same parameters theta for each control task C. Unreal agent optimizes n-step Q-learning loss as shown here. For example, if Unreal agent uses pixel control as one auxiliary reward function, the agent is trained to learn a pixel control policy for maximally changing the pixels in each cell of n by n non-overlapping grid placed over the input image as shown here. This pixel control model, which is trained on the data sampled from a replay buffer. This is a convolutional neural network and this LSTM and this output. The auxiliary network head outputs n ACT by n tensor, namely this Q, AUX, A, I, G. That represents optimal discounted expected change in cell Ig of input image after taking action A, as shown here. Unreal agent removes the perceptual sparsity of rewards and rewarding states to aid the training of agent, but not introduce bias to the agent's policy. Reward prediction predicts the onset of intermediate reward given some historical context. Unreal agent trains the reward prediction task on sequences S tau to predict the reward R tau, and samples S tau from the experience of policy pi in a skewed manner to over-represent rewarding events. For example, zero rewards and non-zero rewards are equally represented, namely probability is 0.5. The reward prediction is trained to minimize loss LRP. Here is a reward prediction model. This is the replay buffer, and this is the output. Reward prediction is not used for anything other than shaping the features of agent. Namely, it biases the reward prediction and the feature shaping, but not the value function or policy. Unreal agent uses multi-class cross-entropy classification loss across three classes, namely zero, positive, and negative reward as shown here. Experience replay is applied to improve the data efficiency and stabilize deep reinforcement learning algorithms. The main idea is to store transitions in a replay buffer and then apply learning updates to sample the transitions from this buffer. Unreal Agent uses replay to perform value function replay, which amounts to resampling recent historical sequences from the behavioral policy distribution and performing actual value function regression in addition to the on-policy value function regression in A3C. Here, there's a value function replay model. This is a replay buffer. The model is trained on data sampled from a replay buffer. This convolutional neural network and this LTSM, this output. By resampling previous experience and randomly varying temporal position of the truncation window over which the n-step return is computed, value function replay performs the value iteration and exploits newly discovered features shaped by reward prediction. Q-learning updates are applied to sampled experience that are drawn from the replay buffer, allow features to be developed extremely efficiently. Unreal Agent combines the primary policy pi trained with A3C and auxiliary task policies pi-c trained on data in the experience replay buffer that are stored and randomly sampled. The primary policy gains efficiency and stability, which is updated online using policy gradient methods. The auxiliary task policies are trained off policy by Q-learning, which allows the representation to be trained with the maximum efficiency. Unreal agent optimizes a single combined loss function with respect to the joint parameters theta of the agent. That combines A3C loss together with auxiliary pixel control loss, auxiliary reward prediction loss, and replayed value loss as shown here, where lambda VR, lambda PC, and lambda RP are weighting factors on the individual loss components. As shown here, this Unreal Agent model, this base A3C agent, which generates this replay buffer. All three auxiliary models are trained on the data sampled from a replay buffer, this pixel control model, this reward prediction model, and this value function replay model. For more details, please check with these references. Thank you. Bye.